Welcome friends, let us start our discussion on Bode Plots. So we have gone through the Bode Plots for type 0 first order system and second order transfer function model. In this sequence we will be discussing few more simple Bode Plot techniques. Then we will discuss a problem on Bode Plots. So today we will discuss on 5 simple transfer functions, that is the integrator or pole at the origin and 0 at the origin, then multiple poles at the origin, multiple zeros at the origin, and the very simple transfer function k divided by nth power of s. So let us start with the Bode plot of integrator. So as the transfer function, you can see this is gs equal to 1 by s, gs equal to 1 by s. So it means g at j omega equal to 1 by j omega, that is equal to nothing but minus j into 1 by omega. So if I want to draw the magnitude of this is 20 log base 10 mod 1 by j omega. So this will become 20 log base 10 modulus of 1 by omega, and the phase will be there for this. So phase angle is phi equals to minus of tan inverse minus of tan inverse. Here you will get 1 by omega is the imaginary part and real part is 0. So this is minus 90 degree. So for an integrator the phase angle is constant and that is minus 90 degree. But at the same time we can find out its slope. So how do you find out the slope of the Bode magnitude? For that you have to take the magnitude for, say here m equals to minus 20 log base 10 mod of omega. So if I take it in this way, that at a given frequency omega 1, m1 equals to minus 20 log base 10 omega 1, this is the modulus, and at the next decade, after a decade, we will see that m2 equals to minus 20 log base 10, this is 10 omega 1, right? So this is nothing but equal to minus 20 log of base 10, that is then 10, then minus 20 log of base 10 mod of omega 1. So as you know that log of a into b equals to log a plus log b. So accordingly we have taken 10 and omega 1 separately. So if I want to find out m2 minus m1, this is equal to minus 20 log of base 10 of 10 minus 20 of log base 10 mod of omega 1, and then m1 is minus minus plus 20 of log base 10 mod of omega 1. So these two terms are cancelled, so I get m2 minus m1 equals to minus 20 log base 10 of 10 equals to minus 20. Again I take another magnitude, m3 equals to next decade minus 20 log base 10 mod of 100 of omega 1. So this one becomes equal to minus 20 log of base 10, 100 minus 20 log of base 10, this is mod of omega 1. So this is again equal to minus 20 log of base 10, this is 10 square minus 20 log of base 10 omega 1. This is again equal to, this 2 square will come in for minus 40 log of base 10 to 10 minus 20 log of base 10 into omega 1, and this is nothing but equal to minus 40 minus 20 log of base 10 mod of omega 1. So from here you can find that m3 minus m2 will again be minus 20. So if we draw the plot in magnitude, you will find that for every frequency, maybe omega 1, 10 omega, 10 omega 1, 100 omega 1, like that, after each decade you will find that there will be a change of frequency by 20 decibels. Here this is minus 20 because this is coming up down. So again, if I go there, this is again from here to here, you will see this is minus 20. So it has a straight slope of minus 20 decibels per decade. So similarly, you can go and find for 0 at the origin. So let us see how 0 at the origin can be worked out. So we can write GS. Your GS equal to S implies that G at J omega equals to J omega. So this magnitude M equals to 20 log base 10 mod of J omega equals to 20 log base 10 omega. So this is the magnitude, and phase angle phi equal to tan inverse of this magnitude is omega and real part is 0, so this is 90 degree. So this is a constant value. Again we can take the frequencies and check. Suppose m1 equals to 20 log of base 10, then omega 1, then m2 equals to 20 log of base 10 omega 1, m3 equals to 20 log of base 10 100 omega 1. Now you find out the difference in the magnitudes, that is m2 minus m1. This is equal to 20 log of base 10, then 10 plus 20 log of base 10 mod omega, and minus m1 is minus 20 of log base 10 mod omega 1. So this is also omega 1. So this is equal to 20 log of base 10 to 10. This is equal to 20 because these two terms will cancel out. Similarly, m3 minus m2 will similarly become 20 log of base 10 to 100 plus 20 log of base 10, 20 log of base 10 mod omega minus 20 log of base 10 into 10 minus 20 log of base 10 omega. So this is equal to 20 into 2 log of 10. These two terms will cancel out, so minus 20 log of 10 into 10. This is equal to 40. Log of 10 is 1, minus 20 log of 10 is 1. This is again 20. So we can see that if we draw the magnitude plot, so omega 1, 10 omega 1, 100 omega 1. So for every say 20, 40, like this, the values will keep on changing at a constant slope. This is 20 decibels per decade. So that is how you can find the 0 at the origin. Next, we'll check if there are multiple poles at the origin, how it will come. So let us check the situation for multiple poles at the origin. So as usual we can write g at s g of s equals to 1 by s power n implies that g of j omega equals to 1 divided by j omega power n, and this is equal to j omega power minus n. So if you take logarithmic of this, so m equals to 20 log base 10 mod of j omega power minus n. This is equal to nothing but minus 20n log of base 10 mod of omega. This is the magnitude, and for phase we should get phase equal to angle of j omega to the power minus n. This is equal to nothing but minus n tan inverse of omega divided by 0 equals to minus n into 90 degree equals to minus 90n, like that. So you can understand that the number of poles at the origin will determine the multiples of the slope for this transfer function. Here this to the power n will go to the front, that is according to Weber's theorem, where the power of the complex number is translated to the multiples of the phase of the complex number. If you have a power of complex number in the form of Cartesian form a plus pi, then if it is written in polar form like c angle d, then the power of the complex number will be translated as the multiples of the phase of the complex number. So let us proceed further. So once we see that this angle is minus 90 degree, so similarly we can find out the slope for this. So let us say m1 equal to 20 log mod of omega 1 to the power n, so we can make it minus 20n to the power n, and m2 equals to minus 20n log of 10 omega 1. So if you take the subtraction of this m2 minus m1, this will give you minus 20n. So it means for every decade of frequency change, there will be the change in magnitude by minus 20n decibels. So accordingly we can find out that the magnitude, if we plot it, so suppose you have omega 1, you have 10 omega 1, so it is, suppose at omega 1 you have minus, suppose at omega 1 you have 0 decibels, then for n equal to 2, suppose we take n equal to 2, so it will be minus 40. So for at omega 1 it will become minus 40 decibels. So it will be like this, so minus 40 decibels per decade. So that is how the slope will be determined, and the phase will be constant to minus 90n. Let us find similarly how the plot of s power n will come. So again we start from the concept. So we shall write g at s equal to s power n implies that g at j omega equals to j omega to the power n. So it means 20 log base 10 mod of magnitude equal to mod of j omega power n. This is mod, so this is equal to 20 log of base 10 mod of omega power n, and this is equal to 20n log of mod omega. Similarly, we can find out the phase phi equal to angle of j omega power n. So this is equal to nothing but, again, by De Moivre's theorem, it will become angle of n into tan inverse omega divided by 0 equals to n into 90 degree. So this will be the phase, and again, if you take the magnitudes at two different frequencies, 20n log of omega 1, and you take m2 equals to 20n log of 10 omega 1, then m2 minus m1 should be equal to 20n. So here again I find that take the magnitude, suppose I am taking here 20, 40, 60, 80, and suppose at omega 1 you have 20, and for n equals to 3 at 10 omega 1 you will have 80. So the plot will be like this, exactly constant 60 decibels per decade. That is how we can draw the magnitude plot, and the phase plot will be simple. Suppose I am getting n equal to 3, so here you have the phase plot 0 degree, 90 degree, 180 degree, 270 degree. So here you will get at omega 1, then at 10 omega 1. So omega 1 you have 0, and omega 10 omega 1 you have 270. So here you will see that the slope will change. The slope of the magnitude will change in 60 decibels per decade, but here you will see that the angle for this will be constant, like this. So this is interestingly in case of integrator and 0, we will get the constant angle instead of varying angle. So accordingly we can draw another example which is little different, and which is the basic problem in drawing the Bode plot. Let us try the example of gs equal to k divided by 2 power n, k divided by s power n. So for here you have to take the gs equal to k divided by s power n, and it means g at j omega equals to k divided by j omega power n. It means this is equal to k into j omega power minus n. It means 20 log base 10 of this is k into j omega power minus n. So this should be equal to 20 log of base 10. So this product will be taken away, separated, 20 log k plus 20 log base 10 j omega power minus n. This is the mod. So here we get equals to 20 log of base 10 k minus j omega, this is minus 20n log of mod omega. So for this, how the Bode plot should come, you can check that this portion will not contribute anything in the phase, but this portion will contribute n into minus 90 degree in the phase. At the same time, the slope will depend on the value of this as well as value of this. That because the contribution in the phase for this is 0, so this will give you a slope of 0 per decade and once you reach the frequency, then you will get the slope of minus 20n. Let us see how. So let us draw the Bode magnitude plot. This is in decibels, in this direction, and this we can take in radians per second in this direction. That is the value of omega. So how the plot should come in this case? So I take the origin over here, 0, 0, then 10, 10, 20, 30, 40 like this, and this is minus 10, minus 20, minus 30, minus 40 like this. So 20 log k, maybe this value can come somewhere here. If I take this here, just by assumption I am taking this value here. So this will be the asymptote for 20k, 20 log k. Now you have to see that the frequency where we will get the second asymptote of value of slope minus 20 n decibels per decade. So suppose this is not the case, suppose you don't have 20 log k, then how this minus 20 n decibels per decade slope asymptote will look like? This will cross the 0 decibel line at omega equals to 1. So here I take, suppose I take omega equals to 10 power 0 and it means 1. This is 10 power minus 1, then this is 10 power 1, that this is 10 power 2. So at 0 decibels, suppose this is the line. So here you are drawing 20 minus 20 n decibels per decade asymptote. So I assume that is n equals to 20. Sorry, assume that n equals to 2. So the slope will be minus 40 decibels per decade, minus 40 decibels per decade. In that case, in 1 decade it should come to minus 40, from 0 to minus 40. So second asymptote should come like this. But because there is a slope 0 asymptote already coming, which is the constant, so these both are added. So I am adding this asymptote 1, this is asymptote 2, so I am adding these both asymptotes. So then it should come something like this. Something like this. So then you can say that your final asymptote should be like this. I mean, final plot, the Bode magnitude plot should be like this. This is also asymptotic, but here, because both are exact plots, so this asymptote is exactly the plot itself. So in this case I can say that this has slope of minus 40 decibels per decade. So that is how you can plot the magnitude Bode plot this. Now we go for the phase plot. So for phase plot, let us see how the phase will appear for this. You have angle of this, I can take angle of the phase equal to, you have the angle for k divided by j omega power n. So this is equal to angle for k and plus angle for 1 by j omega power n. Right, so this is equal to, so for this is the constant, so for this phase is 0, plus for this the angle is minus n times of tan inverse of omega by 0. So this should be, this should be 1 by omega by 0. So this is equal to 0 degree minus n into 90 degree. So this is equal to minus n into 90 degree. So the phase can be drawn easily. You can see that the phase can be drawn easily for this, because it is exactly same as we take, suppose here 0 degree, then here 90 degree, here 180 degree, here 270 degree, and here minus 90 degree, minus 180 degree, minus 270 degree. So in this case, suppose I am taking n equals to 2, then we will have the phase plot exactly as minus 40, so this is minus 2 into 90 is minus 180, so it will come exactly as minus 180 like this. So this one is this one. So for the first one, let us draw it separately. For the two cases, we have, for k the slope is 0, so I am drawing this. For k the slope is 0. This is 10 power 0, 10 power minus 1, 10 power 1, this is 10 power 2. So the phase is 0 for the case of the constant part, and then we see that the other part, that is 1 by j omega power n, that is contributing a phase of minus 180 degree. So it is contributing a phase of minus 180 degree like this. So because both are continuing from minus infinity to plus infinity value, I mean smallest to the largest value, so we can add these two values to get the final value. So if we add these two values, we'll get the final phases like this, like this. So this is how we can draw the phase plot for k divided by s power n. So this much is for today, and in the next lecture we shall discuss an example which will consider different type of factors, that is type 0 transfer function, integrator, as well as the second order system. Together, how we can plot the Bode plot for this. So the textbook is the same by Professor M. Gopal, and the reference books can be referred if you want to explore more examples. And if you find this session useful, you should subscribe the channel, press the like button, set the bell icon, and get the notification. You can send me queries at controlsystemsfaq@gmail.com. Thank you for your patient listening.